Hello everyone, this is your uh, own channel Paper Muni and I'm Bipul Dutta and I'm teaching a quantum mechanics uh, for IITJAM, GATE, NET and other entrance exams for physics. Mm. So this is your 22nd lecture.
Morning, sir.
Good morning.
Good morning, sir.
Good morning. All right. So today now we have been discussing like all the different types of potentials. We have discussed 1D potential, 3D, 2D well potentials, and as well as the quantum harmonic oscillator. All right, so and half harmonic oscillator, and we'll also see how when we have a fermion and a boson given to us, how to make the arrangements and then calculate the energy of the this thing, the system. All right, so we'll come to that, but before going into that, let's discuss another important concept, which is the 0 point energy. So let's begin today's lecture number 22. All right, so now we have this thing that let's write down the topic name: 0 point energy. Okay, 0 point energy. All right, now let's talk about it in the context of 1D infinite potential. All right, so let's take an example and then see an empirical derivation, so to speak. Okay, and then compare it with the actual energy eigenvalue. Okay, we know what the energy eigenvalue of particle in a 1D box is. All right, so let's take this potential. Now in this case we have this potential now infinite. This is infinite at this point, and this region is infinite. Like the potential is infinite in this region, and this is 0 to L, and this is Vx is equal to 0. All right, so this is the potential which we call the 1D box. Now what is, now the question is, what is the maximum uncertainty? What is the maximum uncertainty? Okay, in the position of the particle, in the or of the position in the particle, position of the position of the particle. Okay, so this is the question. Now if you see, if the particle is present somewhere in the box, the maximum uncertainty, it could be of the order of, so we can write like this, that this should be the order of the size of the box. All right, it could be anywhere, so let's say that the maximum, it could be anywhere, like the maximum uncertainty would be L. All right, now we, from uncertainty principle, we have this thing that delta x and px is, let's take it to be h cross. Okay, let's take the equality sign. Now uncertainty in momentum. Okay, uncertainty in momentum. From, we'll calculate it from the uncertainty in position. Okay, so this is delta px, and it's approximately, so let's keep it to be approximate value here. Okay, not a, so this is, if you talk about the approximate values, this is h cross by delta x, right? Now this will be equal to h cross by L, right? So this is, say, equation 1. Now we have the measure, the estimate. This is a rough empirical calculation. Okay, this is not exact calculation. Whatever calculation we are doing is just an approximate calculation, also known as empirical derivation. Okay, so in this case, what we have is, we estimate the minimum energy. estimated minimum energy. Okay, estimated minimum energy. So if you write down E min is equal to, this is px square by 2m. All right. Now, if we find out this delta px, so delta px can be written as what? We know that for a given operator from previous lectures, we know that this is px square minus px whole square. All right. So, and for a potential, we know that for a given potential, if the wave functions are real, the momentum expectation value will be 0. Okay, so using this thing, so we have delta px is equal to root over px mean of px square, and which implies that px square, the mean of px square can be written as the uncertainty in momentum measurement square. All right. So if we write down the minimum energy, this will come out to be delta px. Okay, and this is by 2m, and if we replace delta px value from the equation 1. Okay, so we have this substitution from equation 1. All right, so we have a rough estimate of the energy. We have a rough estimate of the energy of the particle in the ground state. All right, now if we remember the ground state energy which we derived was this, right? So energy of the ground state 1D, we had pi square h cut square by 2 ml square. So it's roughly of the same order. Okay, nearly 10 times, nearly 9 times of this. Okay, so it's we have done a good job for estimating this value. All right, now what does it say? It says that, now let's just note down some points. So note that even at T equal to 0 Kelvin, okay, T equal to 0 Kelvin, for, so this is not okay, this is a Kelvin, this is 0 K. Okay, for a particle in bound state. Okay, we are talking about a bound state. It is only possible for a system to have a minimum energy, minimum 0 point energy, minimum energy or the 0 point energy is it is required that the systems to be bound state. Okay, it cannot be in the unbound state. In unbound state, the energy 0 point energy will be 0. All right, so this is for a bound state only, and the minimum energy is not 0. Okay, the minimum energy is not 0, and the important point to note is this. Okay, so the particle has to be in the bound state first of all, and then if you take the system to 0 Kelvin, then the system will be in its minimum energy configuration, and we find that the minimum energy is not 0. All right, which is the result we have been getting everywhere, like in 1D potential also, in 2D also, and 3D also, and harmonic oscillator potential also. All right, so there is a minimum non-zero value. Okay, so so this energy, the non-zero minimum energy okay, is called zero point energy.
सर सर वो ऊपर एक्सप्रेशन में ई min में नीचे L स्क्वायर होगा
कहाँ पे? अच्छा, sorry. Yeah, you're right. Thank you. Yeah. So in this case, so this is the 0-point energy. All right. So what you see here is, if you can just go through it once more, that if say the particle is in the minimum energy state, it's like, let's put it to 0. Okay, we do not know what will be the energy, but we what we can talk about is that the uncertainty, the maximum uncertainty could be this, and the uncertainty, the value in the uncertainty in this thing, that the momentum will not be 0. Okay, and if the uncertainty in momentum is not 0, then there has to be some energy corresponding to that value of momentum. All right, so this is what we are getting here. Okay, now the next point is, the 0-point energy is the consequence of 0-point energy is a consequence of the Heisenberg uncertainty principle. Uncertainty principle. Okay, so this consequence, this can be explained due to the Heisenberg uncertainty principle. Okay, the presence of 0-point energy. Now for a ground state, okay, 0-point energy is equal to the ground state energy. Okay, now 0-point energy so 0-point energy, or what you can say, for a bound state. Okay, for a bound state, the 0-point energy okay, is equal to the ground state. Okay, so whatever the ground state energy of the system is, okay, for a bound state system, for a bound state in a system is, it will be equal to the 0-point energy. All right, now if we see different potentials which we discussed, which is for 1D box, potential width okay, of width, 1D box width L equal to L. Okay, what is the 0-point energy? ZPE. So this is equal to the energy of the ground state, which is pi square h cut square by 2 ml square. Okay, now this changes with the width. We know that the energy value changes with the width, right? So you have to make sure that what is the width to calculate the 0-point energy. And 0-point energy, just the question might be asked to you like this, that what will happen if you put the system in temperature T equal to 0 Kelvin? Okay, so what is the energy of the system in that case? So it's equal to the 0-point, the ground state energy. All right, it cannot go lower than that. Now for 2D, let's note down something. For 2D box potential, with width Lx is equal to L and Ly is equal to L. All right, so in this case, ZPE is equal to, will be 2 pi. Now this will be 2 square. Okay, now what will be the value of the this thing? If you write down the energy eigenvalue, this is nx ny, this will be pi square h cut square by 2 ml square, and this is nx square plus ny square. So for the ground state, what will be the value? Nx equal to ny equal to 1. Okay, so if you put that value, so what you will get is 2 pi square h cut square by 2 ml square. Okay, now this comes out to be pi square h cut square by ml square. All right, so it just remember the ground state energy for ZPE. All right, now for 1D oscillator, now you can go on for 3D also. 3D will be the ground state. The ZPE for 3D oscillator will be the the ground state energy of the 3D box potential. All right. So in this case, for 1D harmonic oscillator, for 1D harmonic oscillator, all right. So what do we have? So in this case, ZPE will be equal to the energy, ground state energy, okay, which is E naught, and this is equal to half h cross omega. Okay, half h nu, whatever way you like it. Now there's some examples I'll give you, some examples of 0 point energy without. First example is without 0 point motion. Okay, 0 point motion means at 0 Kelvin there is still some motion. It's not that it's completely zero. And without 0 point motion, atoms would not be stable. All right, for electron will fall into the nuclei or the nucleus. Okay, now we are talking about atoms, so let's talk about nuclei. All right, so if you see in hydrogen atom also, there is a ground state energy. Okay, the ground state energy is equal to 0 point energy. So even at 0 Kelvin, the atom remains stable. All right, the electron still keeps revolving around the nuclei. Now the next example is, it is, now this will I will state as a fact. Okay, we'll not get into the details of this statement. Just for your knowledge, or you can say information. Okay, so for a 0 point, so it is the 0 point energy. It is the 0 point energy which prevents. All right, prevents He, helium. Okay, He, helium, from freezing. Okay, at very low temperature. At very low temperature. All right. Now all these are, you can explain using theoretical framework, which is the uncertainty principle. All right. Now let's solve from some problems from previous year. Okay. So we have this thing. Now what we have here is, all right. Now the question which we have here is of oscillator problem. So this is, now let's write down the question. All right. So the question is, this is not related to ZP. This is, you can take it as a revision problem. Okay, so this is a revision problem. Now the question says, if a particle of mass m a particle of mass m all right is moving in or three-dimensional potential, all right, and the potential is given by Vxyz is equal to half m omega square. Now this is given to you as x square plus 2y square plus 4z square. Okay, this is the potential, and what it says that the energy of the particle, the energy of the particle, okay, in the ground state, all right, so this is the lowest energy quantum state. They have mentioned this, that this is the lowest energy quantum state. All right, is, now this is a JNU problem from 2012. Okay, now the options given to you are A, root 7 by 2 h cross omega, B is 3 by 2 h cross omega. Okay, and then C option is 7 by 2 h cross omega, and D option is 3 plus root 2, and this is 2 h cross omega. So this is the question given to you. Now how to solve these kind of problems? Okay, now in this case, if you observe the potential carefully, if you observe the potential and try to remember what we had written for this potential, okay, so this is x square plus 2y square plus, yeah, it's option D. All right, so in this case you have to just arrange the problem in the following way, which is half m omega x square, okay, plus half m omega y square. This is 2y square. We can write like this, right? We are just multiplying this thing as this. Now this one will be, we are separating it out. Okay, we are separating each term out like the way we want it. Now we are writing like this. Now this is omega z square. Now this is 4z square. All right, is there any background noise in my audio?
Yes, sir.
Is it too loud?
No, sir.
No, sir.
Okay, so I cannot do anything about it. It's coming from outside. So let's compare and see. So this omega x is what? Omega. Okay, now tell me whether this is an isotropic oscillator or an anisotropic oscillator.
Anisotropic.
Anisotropic, right? Because the omegas are different here. If you see the terms, if it would have been an isotropic oscillator, then the coefficients here would have been all equal. Okay, if it was a 2 here, it was a 2, it will be a 2 here, it will be a 2 here as well. All right, but it's not, it's different in each case. So omega, this is root 2 omega. Now we are just comparing this and forming this thing. What we have done is we are clubbing things together. We'll take this 2 and club it with this one. We'll take this 4, we'll club it with this. All right, now this is omega z is equal to 2 omega. All right, now this is the omegas which we have. Now if we take the energy for if you want to calculate the energy, what will we get? Now this is ny nz is equal to nx plus half h cross omega x plus ny plus this is the energy given to you, right? Now for ground state, we are talking about the ground state. All right, so what we have here is it will imply that this is nx equal to ny equal to nz equal to 0. Now E 0 0 0. Okay, we're talking all nx, all quantum numbers are 0 here. This will be 1 plus, this will be root 2 plus 2. All right, so this will give us how much? Oh, let's write it the way it is given to us. So this all will be 0. So what we'll have is these values. So this is omega y plus half omega. Now this is z, right? So omega z. Now this will be equal to, now let's put the omegas. Now let's keeping h cross omega here, and inside it will be, this is 1, this will be root 2, okay, and this will be 2. So if you solve this, you'll get 3 plus root 2 by 2 h cross omega. All right. So this is the answer. Right? Everybody is getting this answer. Now there's a question from JNU again. All right. So let me write it down. So this is also from isotropic simple harmonic oscillator. So consider a quantum particle of mass m in a three-dimensional okay, in a three-dimensional isotropic simple harmonic oscillator, isotropic simple harmonic potential, simple harmonic. Now they have mentioned that it is a isotropic potential. If it's not mentioned, then you can figure it out from the potential expression itself. So this is given to you as Vxyz is equal to half m omega square, which is x square plus y square plus z square. All right. Now it is known that the particle is in an energy eigenstate all right, with eigenvalue given to you as E is equal to 7 h cross omega by 2. All right, which of the following cannot be the wave function of the particle, the wave function of the particle. All right, now in this case it's given to you that in the following, now I might require more space. I hope you're writing down the question on your notebook, okay, because it's a little bit lengthy question. Okay, so and h naught, not h naught, this is hn. Okay, hn, this notation is the nth Hermite polynomial, Okay, this is the description given to you. Now let me write down the options. So should I change the screen? Is it okay with everyone?
Yes, sir.
All right. So let me write down the options. So we have this first option, which is h 2, okay, alpha x, this is exponential, okay, this is minus alpha x square plus y square. All right, not x square, this is sorry, this is y square plus z square. This is the first option given to you. Now the next option is h2 alpha x, okay, exponential, this is minus alpha x square plus y square plus z square. Okay, and third option is this is a h1 alpha x, h2 h1 alpha z, okay, h1 alpha z, this is alpha z, and then we have an exponential is minus alpha, okay, now x square plus y square plus z square. Okay, and then d option is h1 alpha x, h1 alpha z, and exponential, okay, there is minus alpha x square plus y square plus z square. All right, so these are the things given to you, and we have to figure out. So can you tell me which option is completely invalid? Just without solving anything, which option is completely invalid?
A.
Yeah, A, because we know that the exponential term, if it's a 3D potential, if it's a 3D oscillator, exponential term will have all the values of x, all the components, like x square will also be present. So x square is missing here. Okay, x square is missing. This cannot be true in any way. So this is, without even calculating, you know this option is wrong. All right. Now let's see the solution. So it says that which cannot be the following wave function. So we can just directly tell without even looking at the question, like rest of the question. Okay, and what is not which one is not a wave function. But let's calculate what could be the wave functions in this case. Okay, it's always good to calculate the detailed solution. Okay, so we have been given the potential to be, this is half omega square, okay, m omega square, and this is x square plus y square plus z square. All right, so let us write the way we write. Okay, now this one is E, the energy with for this will be, now this is isotopic, so we'll write down the energy for this directly. Okay, and here n is equal to nx plus ny plus nz. All right, now n goes from 0, 1, 2, 3. Okay, this is fine with everyone. Now we have been given this energy, this some energy value has been given to us, which is this. The particle is said to be in this state. Now what is this state? If you compare this to, if you compare
N
the,
2.
so n will be equal to 2, right? So this corresponds to this n equal to 2 energy. This corresponds to n equal to 2. All right, so what are the possible this thing possible nx, ny, nz values for this? So this will be, we have already done this for this state. All right, so this was, say we'll have 1 1. Okay, we could have 1 1 0 0 1 1. All right, and then we can have 1 0 1, and then we have 2 0 0 0 0 2 0. Okay, so these are the values which are possible, and this is 0 0 2. All right, now we can see from here that what are the possible eigenstates we can have. Now these will correspond to the polynomials. Okay, and the polynomial will become 1 if it's 0. Okay, for corresponding to the quantum number. So if you try to write down the wave function from here, so this is 1 1 0, so this is proportional to, this will be h1 alpha x. Okay, then this will be h1 alpha y, and for this thing, because it's 0, okay, so for alpha z, and the exponential part will be like this, exponential, okay, minus alpha x square plus y square plus z square. All right, now it has been, they are missing out on 2, So never mind, 2 can be adjusted into alpha. It's already, the alpha is given to be okay. So I think there is there should be some 2 also here. Okay, it's not there here, but never mind, we can adjust the constants. All right, we have to make sure the form is correct. So this is the form. Now you see that this goes to, this becomes 1 because H0 is 1 for any this thing. So this will be 1. So we get rid of this, but we still have these values. Okay, we still have this multiplied to this one. Okay, so we can figure out from which is wrong, because there is a x square missing term, and exponential will have all the components. Okay, no matter what. Okay, so you can see this thing that from A option, now A option is given to us, is A option is, this is alpha x. Now let's analyze each of the options. Okay, let's analyze this. Now B option is H2 alpha x exponential alpha x square plus y square plus z square. Now sometimes it's good to analyze why the other options are wrong. Okay, now wrong, or in this case it's true, but now this is what, this is H0 is equal to 1, and in this case alpha, this is H, what is the option given to you? B, alpha x is given to you. So I think this should be y. Okay, and this would be z. This is 1. All right, now if you have not followed last 2 lectures, then it will be difficult to comprehend this now. Okay, so if you are not able to follow things here now, please look at the other lectures, previous lectures. Now in this case we have this given to us, x square plus y square plus z square. So in this case also we can see that what is happening here is H alpha z is equal to 1. Okay, alpha x actually, not z, this is x. Okay, so this is also correct. It could be a wave function. Now the last option is, last option could be, what was the last option? This is D option. So in this case, for the last option, if we write down the last option, this is H1 alpha x, and we have H1 alpha z. Okay, so in this case we have exponential alpha x square plus y square plus z square. All right, so in what is 1 here? This is 0, alpha y is equal to 1. Okay, so all these are, except this could be the possible wave functions. Okay, the possible wave functions for the state. All right, so what is not possible is this one, and according to the question, this is the correct answer. All right, so that we had already solved it without even solving the problem, but the thing is you should understand all the other options. Sometimes it's not always that all the options are in, like you should analyze it in this type of questions. Okay, now next we'll talk about is Pauli exclusion principle. Pauli exclusion principle. All right, so in this case there, like we did let's talk about fermions. Okay, fermions are what? Particles with half integral spins. Half integral spins. Okay, now let's take an example. So examples, what are the examples you can have? The simple ones, the straightforward ones are electrons. You have electrons. The spin is in this, the spin for this is half, and you have a proton. Okay, so in this case also the spin is half. All right, we can have many examples, but these are the mostly asked particles in a question. Okay, now let's talk about bosons. Now I'm briefly discussing this thing, just stating this thing because we don't require to get into details unless we are into statistics. We are doing statistical mechanics. Okay, so this is the information which we require from this part. So particle with integral spin. Okay, particle with integral spin. Now example could be photon. Now photons, the spin is 1. All right. Now we can have many examples, but these are the 2 examples I've given you. That's it. Now the Pauli exclusion principle, what does it say? Pauli exclusion principle. Now we'll discuss spin in detail when we start for the we'll start with the extra syllabus, which is for the GATE and CSIR-NET. Okay, we don't require it here to discuss the spin in detail. Okay, so Pauli exclusion principle states that two or more than two identical fermions. Okay, identical fermions. Now let's make it not in numeric. Let's make it in 2. Okay, this is 2. Okay, more than 2 identical fermions cannot occupy the same quantum state okay, within a quantum system simultaneously. All right. So basically, energy eigenstate can only be occupied by the 2 identical. If there are identical fermions, then more than 2 cannot occupy the same energy eigenstate. Okay, and we'll see now what happens is in case of fermions with spins. Okay, now why I'm mentioning spin? Now there are sometimes in question it says a spinless fermion. Okay, so the spin is not taken into account. All right, so what we are saying is in case of fermions with spins. Okay, let's treat spins as if some parameter which allows you to place the particles in the state. Okay, which restricts the arrangement of the particle in a given state. Okay, and treat it that way only for now. So the occupancy number in each energy eigenstate. This is 2s plus 1. All right, where s is the spin. Okay, so you should keep in mind this thing while solving problems. Now, if you have this example, say, let's take an example, small simple example. The electron is there and its spin is half. Okay, so what is the occupancy of any given state? Of occupancy will be given by 2s plus 1. Now in a given state, only how many electron can be there? So if you put the value of spin, we'll get 2. So each energy eigenstate can have only 2 electrons. Okay. Now if you take s equal to half, now in this case ms is equal to the components of spin are minus half and plus half. Okay, and where ms is the component of spin, where
Sir,
Yes.
I didn't understand what you said about the two that we got there. So
I said that if you have an energy state,
yes.
what did I write here? In case of fermions with spins, the occupancy number in each eigenstate
Yes.
means if a energy eigenstate is given to you, what is the maximum number of fermion that can be placed in that state? Okay.
Okay.
So if you have an electron, if you have more than 2 electrons, so what is the occupancy that it like if an energy state is given to you, how many electrons can you fill in that? So this is the number of for an electron, only 2 is possible in a given energy state.
Okay. So all right.
Okay.
All right. Thank you, sir.
So ms is component of spin. All right, it's a component of spin. Now let's talk about a question. This is an example problem. So electron.
Sir,
Yes.
sir, please once again repeat this. So you said that we got occupancy for electron as 2, and what was its significance that only 2 electrons can be in?
Yes, if you
same
have a
state?
given state, say if you have a ground
didn't-
state, say you have energy ground state.
Okay.
All right. Now, if you have been given 2 electrons, okay, and then there is first excited state. All right. If you have first excited state, now if you have been given let's say 3 electrons to fill in, okay, now how will you fill? Now what happens is the filling takes place when from starting from the ground state. The filling of electron, when you start placing the electrons in this quantum system of like this, where you say in 1D potential, you are talking about 1D potential of like infinite square, infinite well potential. So in that case, if you place the electron, so 1 electron you can place, say, up spin, and then in this state you can place another electron, okay, which is minus half spin. So though 2
Okay.
possibilities are there, so this fills the state. You cannot place any electron here. Now the third electron, the remaining third electron has to be placed in the first excited state. Now this is how you do the filling. If you had a boson instead of a fermion, then you could have filled for the ground state of the system. You could have filled all the bosons in the ground state itself. Okay, so if you have this thing that this is ground state, now you have 3 bosons. Okay, it could be any particle which are bosons. So you have 3 bosons. So if you want to do a minimum configuration for this, so the first filling will be done on the ground state. So here you don't need to worry about the occupancy number. So you can just place all the 3 bosons together. Okay.
Okay, sir.
Right.
Thank you.
Now we'll be doing the examples. I didn't describe in detail because I will be doing examples now. So it will make more sense. So electron has spin 3/2. Okay, instead of now if you look at the statement of Pauli exclusion principle, what does it say? It says that the 2 or more than 2 identical fermions cannot occupy the same quantum state. When we talk about quantum state, actually we are talking about the energy eigenstate. Energy eigenstate in this case. All right. It could not it did not be energy eigenstate altogether, because it could be that it has to be energy eigenstate. Wait, so let me write it down. Energy eigenstate. Now this state is an energy eigenstate. All right. So if given a eigenstate, how many particles can be there? Okay, can occupy the same state. All right. Now let's take an example where electron has spin 3/2 instead of spin half. Then the number of electrons in an energy eigenstate is. All right. So this is the question to you. Now here there is a hypothetical situation where the question says that instead of electron having a spin half, which is true, let's say it has 3/2. Let's assume. Okay, this is not actually true, but let's assume a hypothetical situation. So the occupancy. Now, how many electrons of with spin 3/2 can occupy a given energy state?
4.
Okay, so you just place the spin value. All right, so you have occupancy number. Now this is 2s plus 1. So this will give you 2 into 3/2 plus 1. This is 4. Okay, so if electron has a spin 3/2, then it would have been possible to accommodate 4 electrons in a given energy state. All right, now let's solve a problem, again an example problem. All right, consider 3 electrons. Consider 3 electrons, okay, in a 1D box potential. All right, in a 1D box potential of width L. Now find the ground state energy of the system. All right, now in this case, let's discuss this problem in detail. So what happens here? Now if it says the ground state energy of the system, it's not talking about the ground state of just the potential box. Okay, the ground state energy of the potential box is the same which we have already calculated, but the system is here that there are 3 electrons in the potential. Okay, not just one particle. So in this case, how do we solve it? So what happens here is, so this one is, say, the potential given to you. Now this is 0 to L. Okay, now it's customary to it's to represent the energy states here. So this is E1. Now let's say there's E2. Okay, now these are the states of the 1D potential, okay, which we have calculated. It has nothing to do with the number of particles in the system. All right, so this is n equal to 2, this is n equal to 1. All right, now this is the ground state, this is the ground state. All right, now in this case what happens? Now if I try to, what is the occupancy for this the electrons? Occupancy will be 2. Each state can have only 2 electrons. All right, so what happens is, if I try to fill in the electrons, so the first electron, we want the ground state energy of the system, so we start filling from the ground state or energy of the ground state system of the potential box. So this is the first, the electron goes here, 1 electron goes here, 1 electron goes here. So we have completed this thing, filling. 1 electron is remaining, so we'll place in the next state. So this is the configuration. Okay, so this whole thing, the arrangement which we have done, this arrangement is known as, we'll say that this is the ground state. This is the ground state configuration of system. This is ground state configuration of system. All right, we are not talking about the potential only, we are talking about the whole system. Ground state of the system. Okay, quantum system. Now quantum system comprises of the potential plus the electrons. Okay, now what happened, the question says what is the ground state energy? Now let's calculate ground state energy of the system. Ground state energy of the system. All right, now this is 2 into, now how many electrons we have? We have 2 in the ground state. So this will be the energy contribution from this part is twice the ground state. All right, 2 into E1 plus 1 electron in the first excited state. So this is the total energy of this system. Okay, now for the ground state configuration. So if we write down these values of the energy E1 and E2, what do we have? This is 2 square pi square h cut square by 2 ml square. Now if we solve this, we'll get 6 pi square h cut square by 2 ml square, or we could write like this. So this is 2 ml square, or we could write like this, 3 pi square h cut square by ml square. All right. So we wanted to calculate the ground state energy of the system where the potential plus the electron forms the system. Okay. Now E1 and E2 is the energy eigenstates of the potential. Okay. So what we needed is just to fill in all the particles starting from the ground state, and slowly, like we put two particles here, 2 electrons here, we are left with 1 electron, we put it in this state, and then this is known as the ground state configuration of the system. Okay, of the system, which system here is 3 electrons plus the potential. All right. Now this is how we calculate the ground state energy of the system. Right. Now let's talk about another example. Now for the same thing, for the same this is say part A. Okay. For the same question, let's have part B. Okay. So the question is find energy of first excited state. First excited state. All right, find energy of the first excited state. All right. So how do we proceed? Now for the same system, we are trying to find out the first excited state. What is the first excited state for this configuration? Okay, first excited state of the system, or what is the energy of the first excited energy of the system? Yeah. So in this case, you have the situation. Now let's fill up see the potential. Okay. So this is the potential, and we have, this is E1 and E2, and let's talk about say E3. Now this is n equal to 1, n equal to 2, n equal to 3. All right, so these are the quantum numbers for the potential, and these are the eigenstates of the potential. Now what we have is we have 3 electrons. Now we know that each state can have 2 electrons. Okay, so let's fill up. Now we have to make sure that it has to be the first excited state of the system. So for the system, what is the next available energy? Okay, so we calculate the ground state energy. So what could be the next arrangement? So we can have 1 electron here, and so this was the configuration earlier, that in the ground state it was this. Okay, now what we are doing is we'll promote this electron to this state. Okay, so we'll take this electron and place it here. All right, so this becomes the next energy eigenstate of the system. All right, because if you calculate the energy of the system, this will be just little bit more than the ground state of the system, which we calculated. So for first excited state, all right, for like first excited state, okay, configuration of the system. Now this is what it is: state configuration of the system. All right, now E is equal to F, say let's write it like this, FES. Okay, first excited system. Now we can see that there's 1 electron in the ground state, which is 1 into E1. Now we have 2 electrons in the first excited state. Okay, so this will be pi square h cut square by 2 ml square plus 2 into 2 square pi square h cut square by 2 ml square. All right, so this will give you 9 pi square h cut square by 2 ml square. So this is the energy of the configuration. Okay, then the first excited state. All right, how did we build the first excited state? We shifted one electron to the next one. Okay, now let's talk about another question.
सर प्रीवियस
Yes,
क्वेश्चन
tell me.
में अगर फास्ट एक्साइटेड स्टेट का एनर्जी निकालने के लिए बोला था तो बस 4 पाई स्क्वायर स्क्वायर 2 ml स्क्वायर होता।
कौन सा विच क्वेश्चन? दिस क्वेश्चन?
यस सर।
नहीं, तो इसमें यही तो सेम क्वेश्चन है ना दोनों में। दिस इज द सेम क्वेश्चन ना, दिस इज रिलेटेड। ओके, दिस इज द सेम।
तो इसमें फास्ट एक्साइटेड स्टेट बोला है तो इसमें एक्साइट क्यों करना पड़ा एक इलेक्ट्रॉन को?
नहीं, तो हमें देखो, कोई एक सिस्टम है, ठीक है, एक सिस्टम है जिसमें वी हैव द पोटेंशियल, वी हैव द सिस्टम इज व्हाट, द इलेक्ट्रॉन एंड द पोटेंशियल। ऑलराइट, दिस इज द सिस्टम वी आर टॉकिंग अबाउट। वी आर नॉट जस्ट टॉकिंग अबाउट द पोटेंशियल, जो द वे वी हैव टॉक्ड अबाउट इन द previous discussions. All right, now we have to take into account the electrons also. So in this case, what we needed is we needed the higher energy, next energy. How do we find the energy of a system? We keep increasing the energy by changing the particle configuration. Okay, so the minimum possible was, the minimum configuration was this. You cannot go beyond below this. You cannot fit this electron into this state. So this is the minimum configuration you can have, for which is the ground state of the system. All right, now what about the higher states? What is the next higher energy? So for next higher energy, we will promote this electron to the next state. Okay, so if I give some energy, the one of the electrons goes to the next state. Okay, so this gives you the next excited state. All right, so this is
Okay,
why we
sir.
did this thing. Now what is the confusion about?
ग्राउंड स्टेट का इलेक्ट्रॉन को क्यों एक्साइट ऊपर क्यों लिया गया, वो थोड़ा डाउट था।
Like ground state ka like we have taken this thing over, like we have shifted this to get the next excited state for the system. That is why we took that electron to this. See, if we don't take this, let's not, this was the ground state, right? This was the ground state. Now what happens is, if you want to get the next excited state, so what can we do? We can shift this electron to this. All right, or we could shift this electron to this, or we could shift this electron to this. Anything could be possible, but what is the minimum next energy you can get after shifting the electron, which is the state which I wrote for you.
ओके सर।
We have to get the next energy level, total energy. How will we get it? We have to give energy to the system, and the electron is excited, it goes to the next state. Now what are the possible states? Now this electron could be the another, goes to third excited state, it could go to fourth excited state, whatever states are available above. Okay, but what is the next minimum? Next minimum will only be possible if we take this one of the electrons in this state, one of the electrons. Now it could be any of the electrons to the next state. All right, so this is why we did this thing. Now if we talk about the second excited state, what could be the second excited state? Now this is the, you can, I have already written it down here, but let me write it here also. This is the first state, first excited state configuration of the system. All right, this is the configuration of the system. Don't treat potential and electrons separately. In this case, we talk about the system. All right, now the next question is, okay, tell me, chalo, let's do a practice problem. Let's if still have a confusion out here, let me do another problem. Now let's talk about what is the second excited state for the system. Let's talk about find energy of second excited state of the system. All right, find the second energy of the second excited state of the system. So tell me, what could be the configuration? if you want to get the next energy value for the system.
The electron will
There-
climb up again.
Yeah.
One electron in each level.
So let's see. No, it could be that way. I'm not denying that, but it could be other way also. So we have to promote the electrons in such a way that we make the minimum change next level. Okay, like it shouldn't be that, okay, if I promote this, now it goes to higher energy, not the next energy. So we have to make sure that, so we had this, so this was the this is the ground state configuration. This was the ground state configuration. Now what we did was for this thing, we have, this is n equal to 1, and this is n equal to 2, and this is say n equal to 3. Now this is E1, E2, E3. Okay, now these values, you should make sure this is the energy eigenvalues of the potential, energy eigenvalues of potential, not the system. Okay, now in this, the first state configuration, what we did was we promoted one electron upward. So this is the first excited state. All right, now we are talking about the second excited state. What could be the second excited state? How will the configuration look like? So this is the ground state configuration. This is the ground state configuration of the system. This is the first excited state configuration of the system. All right, this is the first excited state configuration of the system. Now, if we try to find out the next energy configuration, is n equal to 1, n equal to 2, n equal to 3. All right, so these are all 0 to L. So what could be the possibility? Now energy in this, what did we get? What was energy in this? Please tell me. The first, the ground state configuration.
6 pi square h square by 2 ml
6 pi
square.
square h cut square by
2
2
ml square.
ml square. What was the energy for this?
9 pi square h
9 pi square
H cut square.
So you don't need to, there is no formula. Don't try to remember these things. So this is 9 pi square h cut square divided by 2 ml square, right? Now let's talk about this system. So what could be the next state? You are saying, somebody said that we should promote this to this. So calculate the energy in that case. Calculate the energy in that case. Or what could we do? What can be done for this? Yeah, tell me.
Sir, can we use the concept that with increase in the levels, the energy difference increases? So we'll shift the electrons so as to make the minimum change.
Yeah, that is what we are using here. Okay, that is what we are using here. We are trying to get the next minimum energy. Okay, so if we, so what you are saying is 14.
Yes, sir.
All right, so anybody else? So let's say, what are the possibilities? We can shift this to this. Okay, so in that case, what will you get? 9 plus this will be 9 plus this will be 2. This will be 2 plus 2 square, 2 square. So this will be 8, 17. This becomes 17, right? If I shift this to this, the energy will become 17 times of this thing, the ground state of the E1, like the E1. Okay, so you can just think of it like that. Now this is not possible. Now what can we do next? What is possible? We could take this electron. We could take this electron and place it here. Okay, so what is the energy there? You have 3 square plus 2 square plus 1. So this is 14, right? 14 E1. So 14 E1 is the next energy we have. What else could we do? We could have taken this to this. So it's the same thing. It will give you the same thing, right? So what we see is that if I shift this to this, we get a very, like the energy is more than this change. All right. So we'll stick to this thing that the next energy level could be, if we shift this to, if we shift this electron, now let it be this here, this is here, and this will go to this position. Okay. So in this configuration, if we write down, this is the second excited. So let's write it like this: second excited state, second excited state configuration. All right. So in this case, say this is SES. All right. Or let's write it not this way. There's no standard abbreviation. So second excited state. So in this case, what can we do? We can just multiply 1 into E1 plus 1 into E2 plus 1 into E3. All right. So what we'll get is, we'll get pi square, h cut square is common for all this term. So what we have, 1 square plus 2 square plus 3 square. So this gives us 14 pi square h cut square by 2 ml square. All right. So this is how you can go on, and you can keep finding the next energy available. All right, for the system. Clear? I hope everything is clear now. Now the question is, next question is based on the 3D or 3D potential. Okay, now let's see how we treat higher dimensional potentials. So consider 6 electrons in a 3D cubic box potential. 3D cubic box potential means this is all isotropic. Okay. Now of side L. All right. Now find the ground state energy of the system. Energy of the system. Now how we draw this thing, how we build the system, like how do we show it. All right. So what we can do is, we don't like draw the box and to show you the things. So what we know about the 3D system, we know that energy eigenstates are degenerate. Okay, for cubic system we have a degeneracy, so we have to make sure that we take into account that. All right. So E1, what is the degeneracy for E1? 1, right? For the 3D cubic box, what is the degeneracy of first ground state of the potential? So that is 1. So G is equal to 1. So we'll have 1 eigenstates available for this energy. Now, if you talk about the first excited state, what is the degeneracy here? What is the degeneracy for the first excited state? 3. So we'll have 3 states at the same energy level. Okay, we have 3 states in the same energy level. So how do we fill? We have 6 electrons. So filling starts from the ground state. So we fill 2 electrons here, and we could fill any of them. Now there is no this thing half filled, full filled configuration. We are not talking about stability here. We're just trying to get the energy. So it did not be like you fill 1 1 1 and then you fill like that. It's not like that. Just it will give you the same result. We are talking about the energy. Okay. So in this case, let's fill this this state with 2 electrons. Now we are remaining 2. So we could put anywhere. So let's put it here. All right. So this has nothing to do with the half filled and full filled structure. All right. So you could have placed it anywhere like this. You'll still get the same answer. Right. So for this, we can, now this configuration is called, we'll call it the ground state energy of the system. All right. So the ground state energy of the system is equal to, this is 2 into E11 plus E211. So we could have mentioned anything. We could have mentioned we could have mentioned anything here. Okay, so this is E211 or 121, any of them. So now this is 4 times this value. All right, this is 4 times this value. All right. Yes.
So here in E2, are we not violating the exclusion principle? I just don't understand how you do that, sir.
No, because we have 3 eigenstates possible, right, for a given energy.
How is it different from the one we drew the last time, sir? For the
So this is a 3D box. This is
Okay.
a 3D box.
Yeah, the
And
degeneracy is 3. I get that, sir.
uh,
But how can we do that? I just
what is the state available? What is the number of states available in each state here for each energy for 1D box?
2, sir.
No, energy state. What is the degeneracy of this state, this energy? What is the degeneracy of this ground state?
1.
So we have one state, right?
Yes.
So that will be filled up with these 2 electrons.
Okay.
Okay, we do not have any other state.
All right. So if
Alright.
the degeneracy increases, you'll draw more like that.
We are
correct?
talking about the Eigen state. We are talking about the Eigen state. We are not talking about just the energy.
Okay. All right.
We are talking about the state, right? That is the keyword.
All right. Sir.
So here we have 3 states available. Electron could be in any of the states.
All right.
Right.
The same level. All right.
All right. So if you write this, so this will be 3 pi square h cut square by 2 ml square plus 4, okay, into 6 pi square h cut square by 2 ml square. All right. So if you solve them, you'll get this is equal to what is the value you're getting? 6 plus 24, 30, 30 by 2. So this is 15 pi square h cut square by ml square. So this is the answer to our question. All right. So if you want to calculate the first excited state, you can go ahead. You can take it as a homework. All right. So you can calculate the first excited state of this system.
I'm sorry,
Go on.
sir. Can I ask something?
Yes.
Sir, why did we write E211 here?
E211 actually it could be any of the states. No, it could be
Yes,
like,
all states they have the equal energy value.
yeah. So if in this case, and what is this state? This is say let's write it like this. Now this is we cannot write E1 because it will make no sense. So what we have is this is 1 1 1 nx equal to 1 nx and y equal to 1 and z equal to 1. In this case, we could write like this. We could write any of the this thing like this, that 2 1 1 or 2 1 2 1 or 2 1 1 2. All right, any of it is possible. All right. So just to make it easier to visualize things, okay, I just wrote it like this.
सर तीनों डिजेनरेट स्टेट में से किसी एक को ही लिखना है.
हाँ, मतलब लिखना क्या है? Just मैंने notation लिखा है. Like it's like the notation. Say let's talk about this thing. I'm using the notation for this ground state as this. For this, I'm using this. So this is 2 1 1. Say this is 1 2 1. This is 1 1 2. All right. This is 1 1 1. So this is like this is the ground state. This is the first excited state. I'm labeling it like this. I can always change the labels. Okay. So just for reference, because I cannot fit so many values here. If we have a state where there are 6 the degeneracy is 6, how will you write that thing in the diagram? Okay. So this is how I'm labeling it. That this, let's call this energy level to be E2. Okay. So this could be any of them. So we are just taking the value. We are concerned about the value of this state. Okay, this could be E121. This could be E112. All right. So all have same values. So we know that E121 is equal to E112 equal to E211. All right. So it could be any value.
Sir.
Yes.
Sir, if the length, breadth, and height of the potential box were not same, so then it would not be degenerate, na?
Yes, that is what I have already said to you in the previous lectures.
So then how we determine which one is the first excited state, second and third?
In which case?
Then
in this case,
so
or
in 3D
you are talking
box,
about a rectangular box?
Yes, sir. I'm talking about rectangular box, sir, because there is some confusion while writing
So
the
I'll
states
discuss.
in
I
that.
had given you a homework problem. Okay, I had given you a homework problem which was from JNU. Which some of you have solved already, and some of you still have doubts. So we'll discuss that problem. Okay. So how to talk about it? Okay, let's take that question and let's discuss it right now. And then which lecture it was? Do you remember that? which lecture was the question from? So this is the 3D box. Now, which can anybody help me with this thing? Which lecture it was from? I don't exactly remember. So you have, this was given to you, fine. Now this was the,
No, sir, it was before this. Around 15 or 16.
16.
Just check.
Okay, so let's, no, just if you give me the exact lecture, the date or something like that, I can directly go to the question, or else we'll lose some time. So this was done, this is not there. So I think somewhere in the middle the question was being asked. All right, so that's why I'm not able to get the
Sir,
question.
it was asked at the last of the lecture. It was
2
for
lectures
the whole
before
lecture.
linear harmonic oscillator started.
Okay, so this is a 3D rectangular box. So I think we have not asked in this lecture. Okay, so this is I think this was the last question in this section. Now let's see this thing. So yeah, this is the question. Yeah, so let's discuss this question. Oops. Let's take this question and discuss it. That will clarify all your why am I cutting it? No, this is the question. All right. Yeah. So it says that you have this state now, this configuration. We already know this, what the question was. So let's discuss this. What is the energy of the second excited state of a particle of mass m moving freely inside a rectangular parallelepiped of sides L, 2L, 3L? All right. So we have this thing given to us. Now let's see the solution. All right. So how will you do it? Now let's write down what is the, we don't have to write down the potential. It's already, since you have practiced a lot, you already can see what the potential is. What we can write down is the energy. Now, what is the energy eigenvalue in this case? Okay, nx, ny, nz. So this can be written as, now the common term is the pi square h squared square by 2 ml. And now we don't have the L here, okay, because we cannot take out the L here. What we had is this thing, ny square by ly square, all right, plus nz square by lz square. All right, so this is the energy. Now what are the values given to you? Lx is given to you as, Lx is L, Ly is 2L, and Lz is 3L. Lz is 3L. All right, so this is what we have. Now the thing is, we can write this down. Now this is, I wanted to discuss how to get the calculation easily done, because if you rearrange the expression which you get for energy by putting in the values of L, you can easily get whatever states you want. So this is L square plus ny square by 2L whole square. All right.
Sure.
This is plus, this is nz square by 3L square. Okay. Now this is the expression for energy which you get. Now we can simplify it further.
Sir?
Yes.
Sir, are we just assuming the dimensions, because they haven't mentioned which one it is for, right?
Sorry.
Like you're assuming that L is for the length along the x direction. They haven't said anything about that, right?
No, it is. You have to be going like you should go like this only. All right.
Okay. Okay.
Not mentioned, but how do you write down the? You have some this thing, no? A customary practice to write the lengths in the serial order. Okay.
All right.
Because if you try to make, now you will be changing nx values. You would like that. Okay, let's start with the nx values. So it would not make sense. Okay, you could have taken any length, any direction. Okay, but what we require is what is the next minimum energy? What is the what we are talking about is the ground second excited state. So you can't change the order, but you have to be very careful with that. Okay, so that is why I'm not changing the order. We are taking it as it is. So we have nx square plus this is ny square by 4 plus nz square by 9. All right, now it's difficult to discuss this thing. Not difficult if you observe it carefully. You can just keep on changing the values and you'll get the answer. But still, the better option is if I may take the LCM. If I take the LCM, what do we get? So we have this 36 out here, so we'll get 72 ml square outside, and here we'll have 36 nx square plus this is 9 ny square plus this is 4 nz square. Right, this is what we should get. Is this clear? We are just now took the LCM. Now you can see one thing. Now from here it becomes very clear which values to change, which values to change to get us the next minimum energy. All right, so if you see, if you write down nx, ny and nz, so you cannot change nx in any way. You have to keep it to be minimum. You have to keep the nx value to be minimum to keep the energy minimum. So if you talk about the ground state, so let's talk about the state, which state it is. We want to find out the ground state. So what is the minimum ground state? So we all know it could be, it has to be 1 1 1. We have no other option. Okay, we cannot go to 0. It's not, 0 is not available. Okay, so we have 1 1 1. So what is the energy here? Energy in this case will be, let's write down, this is the ground state. So energy will be E111. This will give us, so in this case, what we'll get? This will be 36 plus 9 plus 4. So this is 49. 49 pi square by h cut square by 722 ml square. Right? Is it everyone is getting this result? Now, what is the first excited state? First excited state. So what are the values you can have? You cannot increase nx. If you increase nx, it will shoot up because the coefficient is huge. If you increase ny, it again shoot up. All right, but less than nx. The impact is less than nx. Okay. Now in this case, if you have this one, if you change this value, then it has the minimum effect in the change. Right. So what we'll do is we'll keep nx as 1, ny as 1. We'll change this to 2. So this is the state. What we have is the next state. So if you add them up, so this is 36. Let's slide it down. So I'll just write down the answer directly. So this is, because it will become cluttered here. So this is ml square. Now what is the value? 36 plus 9 plus 16. 36 plus 9 plus 16. Okay, we have 2 squares of 2 square into 4. This is 16. So what will we have? This is 21, 1, this is 2, this will be 6. So what we have here is 61. The value is 61 pi square h cut square. So this makes a better, easier way to do it, to get the feel of how to select the next energy level. All right. So I wanted to show you this thing. So now the second excited state. Okay, second excited state. Now, what is the next energy level we could change? We could change the value of n. We cannot change in any way the value of nx. It will take some time to change the value of nx because the coefficient is too high. All right, it's 36 times. What if you change a little bit, it will blow up. So we have to decide which one to change. Now, is it ny or is it nz? What will give us the next minimum? So if I change ny, what will happen here? If I change ny to 2, so we have 36 from the nx, this coefficient, 36 from here. The contribution from ny, if I change ny to 2, so what will happen? 9 into 4, so this is 36 again, and this will be, let's keep nz to be 1. So this will be, okay, this will be 4. So what will we get? We'll get 76. All right. So what is the next energy available? Let's talk about, instead of changing this thing, instead of changing ny, let's change nz. So in that case, so in this case, what we have done is we have changed, put ny is equal to this thing, ny equal to 2, and nx is equal to 1, and nz equal to 1. All right. Now let's talk about, say, nx equal to 1, and we have nz equal to, instead of 2, let's put it to be 3, and ny is equal to, let's say it is 1. Okay. So in that case, what will happen? It will happen that like we'll get the result is 36 plus 9, okay, plus 4 into this thing, 4 into 3 square. So this will give us how much? So 4 into 9 is 36. So if you add them, you already see this, that you have, what is the value here? You have 72 plus this is 81. All right. So which value should you take? Which value should you take from here? So what we have here is, we have to take the next minimum. Next minimum is how much? This one. Okay. So the values will be, this is n1, this is 1, 2, and this will be 1. So in this case, we have 1, 2, 1. Okay. So this will give us, what is the value? We have 76 pi square h cut square by 72 ml square. Okay. So what is the answer? If you simplify it further, if you see the options, what is the given? What is given to us? So if I divide it by, now if I divide it by 2, we'll get 36. So 76. Now this will be 38 by 36. All right. Now there's some. Did I do a calculation mistake here? Anyone is getting any other result? So this is 36 plus 9 plus 4. All right. So what we are getting here is, first step will be 36 plus 9. This is 45 plus 4, 49. That is fine. Now what we did, what we had here is 36 into 2, so 72. That is fine. So the first state is good. Second state is we have 36 plus 9, which is 45. 45 plus 16. So we have 61. That is correct. So we wanted a second state, right? Second excited state. So this will give us, now if we choose from which one to follow, this will give us how much? This will be nx equal to 1, nz equal to 1, ny equal to 2, and we'll get 36 plus like 9 into 4 is 36 again, and then we keep it 1. Okay, so this is 4. So this is 72, 76. That is fine. Now what else do we have? Now this one will be, this is 36 plus this thing, that 9 into 1. So this is 9. Now we have, again, instead of this thing, if you put 3 square, so 4 into 9 will give you 36. So 36 is 72. 72 plus 9 is 81. So we have to choose this thing. This is fine. So I think the answer is somewhat not, the options are not matching here. So what is the value we are getting? If you simplify this further, you'll get this to be 9, 19. Okay, and this one to be, and this is, there's some 2 factor missing out here. All right.
Sir, can you please show once again your calculation? Actually,
I got 122 as the answer in this.
For what?
Second excited state, this question. 11 by 30, 11 h square by 36 ml square.
How is it? What are the values of nx, ny, nz?
122.
122.
Hmm.
What about 121?
It
What
is
about
same as
121?
first excited state and second. 112 and 121 is same.
ये तो
No,
first
it's not same, no, because it's a rectangular potential. It cannot be degenerate. It cannot be degenerate. Degeneracy will not be
Okay,
here.
sir.
There won't be anything. The degeneracy is not here. Please don't get confused with this thing. This is a rectangular paper. All sides are different. Okay, there's no degeneracy here. So these are the calculations I have. All right. So I think I made some mistake out here. Now you're talking about 122. Now
Yes,
122
sir.
will blow up. 122 will blow up, right? 122 will be more than this value.
Sir, I am getting 19 h square by 72 l square. for 1 to 1.
1 to 1. So I think I made a mistake out here somewhere. So tell me what are, so if we put the values here, so 36 plus 9 into 4, 36, right? So 36 plus 36, 72, 72 plus 4, 76. So 76 by 72. That is what I'm getting.
Sir, I did like pi square h cut square by 2m. Then I did 1 by L square in bracket 1 by L square plus 4 by 4L square plus 1 by 9
Our
L
answers
square.
were in terms of h square.
Okay, h square. All right, all right. That is why I'm making like I'm getting confused. So
Yes,
if you place this thing, I didn't see that. Okay, great. So this is 76 pi. Now let's get rid of the pi. Now it's everything is fine. That is, I thought it was h cross square. So this is h. All right, h square. Now here what we'll have is we'll get 4 here. Okay, so if you cancel this out, so you'll get 19 by 72 h square by ml square. Yeah, I didn't follow that thing. Now this is correct. So we have this answer to be this thing. All right, D option. D option is correct. D is correct. So sometimes, see, I also made a mistake here. I didn't see that it was h square. Okay. So if you, whenever you see some point like mistake, don't wait for me to clarify that. Just speak up. Okay, so that the time is saved. All right. So yeah, this is the answer. That is why I'm what I was thinking. Why is it wrong? Everything is correct. Okay. All right. So this is the answer. Now 1 to 2 is it will give you a higher energy. All right, than this. Okay. So I hope let's sign off then. Thank you for watching. Have a great day.
Thank you, sir.
All right.
Thank you, sir.
Hello, sir.
Yes, tell me.
Sir, you were saying that you will have a session on about the preparation.
Yeah,
in 2
I
months.
said that. I said that, but let's plan it someday. So I'll keep the lectures in the morning. All right. And
Okay, sir.
what is the date of IITJAM?
14th Feb.
14th Feb. No, so you don't you still have time. So it's not yet 2 months. What is it?
Sir,
December, January, February. You have, what is the date today? It is 8th, right? So we still have 1 week. So we'll fix somewhere in between. We'll talk about it. I'll keep a 1 hour session for that. Or I'm also thinking to bring in some students who are in IIT Bombay or IIT Delhi, so you can interact with them directly. All right, let's see. I'll talk to them. Okay, if they have time.
sir, so the
Yes.
classes
Sir,
are going to be in the morning from now on.
Yeah, it will be morning because I'm short on time. All right. So since I have committed to completing this course, all right, so I have to adjust in this way. And see, the lectures are already available in YouTube. Okay, so if you miss the lecture, you can always see from there.
All right, sir.
All right, so don't worry about it, because I have time restrictions. I have to adjust things that way, or else I have to cancel all the classes.
Okay, sir. All
Which
right.
is not a possibility I think of. Okay. So okay, thanks for watching. Have a great day. All right.
thank you, sir.